Hello everybody, and welcome back to another. In this tutorial, we're going to be covering quiz number 30, which wraps up the applications of virtual work. Now, can you guys believe it's already been 30 quizzes? 30 quizzes, and we're at this point. Only 3 more quizzes to go, as you guys are going to see. They're not too bad. They all deal with the Rayleigh-Ritz method, which is, in my opinion, just an easier version of virtual work. I never really liked virtual work, but the Rayleigh-Ritz method's a lot of fun, and you guys will get it, no problem at all. You guys are so smart, and you guys have made my life so much easier dealing with my stupidity over the semester, so I thank you guys all for that. Now, before we begin, a couple of notes. There's not really any theory to this quiz, so we're just going to go through it. The theory of virtual work is that the internal virtual work is equal to the external virtual work. You guys are experts at that, no problem at all. All the equations you guys need will be presented, so it's going to be nothing really too new or too crazy. Now, the big note I want to talk about is I really changed the format of this quiz. I'm not sure if you guys are going to like it. I'm going to be completely honest with you guys. I have no idea. I don't know if it's too over the top or anything about it, really. So please let me know what you guys think. If you guys prefer this method and you guys think that this is the way to go to best help you guys understand the questions, then I'm going to stick to this method. Again, this is always to help you guys make the learning experience as best as possible for you guys. If you guys hate this method and say, Clayton, why the hell did you do this? Go back. Don't worry, I will go back immediately for the remainder of the quizzes. So you guys just let me know. Whatever you guys like, that's what will happen. So thank you guys for the feedback. I look forward to hearing about it. And I guess with that being said, let's jump into the quiz. Alrighty guys, welcome to the quiz. As you guys will see, the quiz is going to be 6 questions, and it's a really good quiz because these are exactly the type of questions you can expect on your final. Now looking at question number 1 here, it says the shown cuboid is subjected to a state of stress described by the Cauchy stress tensor, and it gives us that nice Cauchy stress tensor, nothing too crazy thus far. Luckily for us too, it also gives us a nice diagram of the cuboid, which is good and bad because we have a diagram to reference, which is nice. However, it's bad because it's a little bit complicated, so this may overwhelm some students. Now, the question itself says a virtual displacement field of U star, so the virtual displacement field, is equal to A times x1, and then A times x1 squared, and then 0, where A is greater than 0 is applied to the cuboid. Then the external virtual work due to the traction vector on face ADFE is given by, and of course we have our 4 options. Now, the first thing that we're going to have to take a look at, traction vector. The question says it wants the virtual work due to a traction vector, therefore we know automatically, right away, we're going to need that traction vector. However, the question does not give us the traction vector, so we know we're going to have to solve it. So the first thing that the question does give us is it wants it on face ADFE. So if we look at our diagram of the cuboid, we can kind of shade in that face and get a good idea of, okay, where exactly is my traction vector going to be located? Now you guys may not remember, but in order to calculate a traction vector, one of the most key pieces of information that we need is the normal vector of that surface. What do I mean by that? Well, I mean something like this, where if we look at that surface, I have a normal vector pointing away from that surface. Now this normal vector must be perpendicular to that surface. So now if we have our little chalkboard here, the question becomes, all right, how do we solve this question? Well, the first thing that we always mention is we need a traction vector. In order to do that, we need a normal vector. So I'm going to start off by saying, all right, well, how do we find the normal vector? Well, it's pretty easy because we remember that the normal vector points away from the surface, meaning that it's perpendicular to that surface. Now, if we look at this surface, it's in the x2, x3 plane. Therefore, we know that this normal vector is going to run parallel in the x1 direction. So we know that our normal vector in this case is simply just going to be 1, 0, 0, because again, it's running parallel with that x1 direction. Now keep in mind that the normal vector is also a unit vector, therefore the magnitude also has to be 1. So if you had a normal vector of, let's say, 2, 0, 0, that's actually incorrect because it is not normalized. We need to normalize it. So in this case, our normal vector is going to be 1, 0, 0. Now this is great because once we have that normal vector, we can move on to determining the traction vector, which is going to be the key in which we need to determine that external virtual work. So in order to do this, well, not too bad. We have a nice formula. We recall that the traction vector formula is simply the transpose of the stress tensor multiplied by that normal vector. So we take a quicker look at this. Well, the stress tensor, we have that. We have it circled in green over there on the right. And then the normal vector, well, we have that too. We have it circled in green just right above there. So that's not going to be a problem for you guys. The question becomes, hold on, Clayton, what is this x1 equals 2? Well, if we look at that surface, we can see that the whole surface in this case is located at a value of x1 is equal to 2. So since we know that, any calculation that involves x1, we're going to substitute x1 is equal to 2 in all of those equations, and you guys will see what I mean shortly. So since we know the stress tensor as well as the normal vector, we can substitute them into this equation to get the following. Now, if we look at that stress tensor, I have a neon blue 2 in there, and you say, Clayton, where did that come from? Well, if we look at the stress tensor on the right, that's stress component sigma 1, 1, which is simply x1, well, we know that x1 is equal to 2, so I just substitute 2 in for x1. All the other components in our stress tensor are functions of x2, so therefore we need no substitution, but that first component, sigma 1, 1, it is x1, so we have to substitute it as 2. The normal vector, on the other hand, it's just 1, 0, 0, no simplification is needed. So after we get to this point, we simply have our matrix multiplied by a vector, and we can solve, and what we get is our traction vector is equal to 2, x2, and 0. So this is going to be the first big step determining what that traction vector is. After this, it's pretty easy. So with the traction vector known, we can go right away into determining what the external virtual work due to a traction vector is. And again, that's what the question wants, the external virtual work due to a traction vector. Now, in its actual definition, it looks pretty ugly. So the external virtual work due to a traction vector is a surface integral of the traction vector dotted with that virtual displacement vector. Now, the key here is dotted, and we're going to talk about that a little bit later. First things first, I don't know about you guys, but I hate surface integrals. They look ugly. I don't really know what it means. I'm integrating over the partial domain with respect to ds. That means nothing to me. So the first thing I want to do is simplify this into a form in which I do know. So what we do know is if we look at that surface there, it is actually in the x3, x2 plane. So therefore, the only real things I need to integrate over are going to be dx2 as well as dx3. Now, where does x1 come in? Well, just like the traction vector before, we know that the entire surface is actually located at a value x1 is equal to 2. So if we ever have an x1 in our equations, we're simply going to substitute that with the value 2 and carry on our way. So it's not looking too bad so far. So if we look at the components which we need inside of this integral, well, we know all the components. The first one's the traction vector, which we have right above us because we just solved for it. And the second one is that virtual displacement vector. Now, it's not obvious looking at the work where this is, but if we actually look into the question description, we have it circled in green. Luckily for us, they actually give us the virtual displacement field, where u star is equal to ax1 squared, and 0. So what I'm going to do is I'm going to substitute both the traction vectors as well as the virtual displacement field into our equation, and we get the following, where we have the double integral from 0 to 1, 0 to 1 with respect to dx2, dx3, and inside we have our two vectors. Now, I don't know about you guys, but if I were doing the math class and I see two vectors like this, I'm thinking, well, what the hell? How am I supposed to integrate a vector? Now, this is the key that I told you guys about before, is what we're doing with those two vectors is we're dotting them together. So if you guys may remember, after the dot product, our two vectors become a simple scalar. So if we move a step forward after we take the dot product, we see that those two vectors actually simplify into simply 4a plus 4ax2. How did I get this? Well, if we look at our two vectors, the first component of the traction vector is 2. The first component of the virtual displacement field is 2a. So we got 2a multiplied by 2, that gives us 4a. Similarly, we can look at the second component. We have x2 multiplied by a times 4, well, we get 4a. It's really simple. We have our double integral. Everything is defined. There is no unknowns. We can simply solve for it. And what we get is the external virtual work is equal to 6a. Now, if we look at our possible answers, we see that the first one is 0. Well, that's not true. The second one is 3a. Well, that's close, but not quite. But if we look at C, 4a, getting a little bit closer, but finally if we look at D, we can see that answer D is 6a. 6a is what we determined, so we can conclude that D is our final answer, where the external virtual work due to the traction vector on the face ADFE is simply 6a. So as you guys can see, not too bad of a question, and I really took my sweet time with it, but of course in a final scenario, you guys will be rushing through this like crazy, and it's not too bad at all. Alright, let's move on to question number 2. Alright guys, welcome to question number 2. As you guys are going to see, question number 2 is very similar to question number 1, with one little change, but of course that change leads to everything else changing, making this a completely different question even though it appears the exact same. So question number 2 says, the shown cuboid is subjected to a state of stress described by the Cauchy stress tensor. So if we look, we have a nice 3x3 Cauchy stress tensor, nothing too crazy. And if we compare it back to question number 1, we can see it's actually more simple in the fact that we have a lot of the x2 terms removed from this stress tensor. Now the question says, if a virtual displacement field of u star, which is equal to 0, ax2, and 0, where a is greater than 0, is applied to the cuboid, then the external virtual work due to the body forces vector is given by, and of course it gives us our 4 options. Now, what's nice for us, external virtual work, it's actually not that bad to calculate for a body forces vector. But the key here is a body forces vector. And if we look at the question, well, we're actually not given what the body forces vector is. So just like question number 1, where it wanted that traction vector and we weren't given that traction vector, you guys are going to see that the first step in these types of questions are going to say, all right, what does it want and how can I calculate it? So it wants the body force vector in this case. I don't know what that is. So my first thing that, of course, I'm going to need to do, calculate what that body force vector is. Now, if you guys remember from equilibrium, we had those nice equilibrium equations. There was 3 of them. Now, with each equilibrium equation, we can solve for a single component of that body force vector. So we're basically going to solve 3 equations for 3 unknowns, and once we do that, we'll have the 3 components, and once we have the 3 components, we can put it into a vector form. Now, it sounds kind of crazy, but it's actually very simple. So if we look at the first component of the body force vector, which I call rho b1, it's simply negative of the partial derivative of sigma 1,1 with respect to x1, minus the partial derivative of sigma 2,1 with respect to x2, minus the partial derivative of sigma 3,1 with respect to x3. So the key here is if we're looking at sigma 1,1, sigma 2,1, and sigma 3,1, and compare it to our stress tensor, we can see that we're actually going down a column of the stress tensor and not across a row. However, the partial derivatives, it's actually pretty simple to calculate. So if we go through this equation and simply going down the first column of the stress tensor, our first component is the partial derivative of sigma 1,1 with respect to x1. Well, if we look at sigma 1,1, it's negative 2 multiplied by x1. So if I take the partial derivative of that bad boy with respect to x1, I'm simply getting negative 2. Moving on to the next component, which is 5. Well, if I take the partial derivative of 5 with respect to anything, it's going to be 0. So that's going to be 0. And similarly for the bottom component, sigma 3,1, which is 0. If I take the partial derivative of that, well, I'm going to get 0 as well. So in the end, we can calculate our first body force component, rho b1, as simply minus negative 2 minus 0 minus 0. So this is just going to be 2. Moving on, we can find the second components of our body force vector using the same methodology above. Remember, these are just a manipulation of the equilibrium equations. So it's going to be negative multiplied by the partial derivative of sigma 1,2 with respect to x1 minus the partial derivative of sigma 2,2 with respect to x2 minus the partial derivative of sigma 3,2 with respect to x3. Now this one's even simpler because if we look down that middle column, it's all constants. Sigma 1,2 is equal to 5, sigma 2,2 is equal to 3, and sigma 3,2 is equal to 0. Now if we have a constant, we take the partial derivative, it doesn't matter what it's respect to, it's going to be 0. So in this case we have 0 minus 0 minus 0. Well, of course that's just going to be 0. Finally, we can move on to the third component of the body force vector, which is rho b3, and it's simply the negative of the partial derivative of sigma 1,3 with respect to x1 minus the partial derivative of sigma 2,3 with respect to x2 minus the partial derivative of sigma 3,3 with respect to x3. And just like before, if we were to look at that last column going down, it's just a bunch of constants. And in this case, it's 0. Well, again, just like row B2, if we ever have a bunch of constants and we take the partial derivatives, well, it's just going to be 0. Therefore, row B3 is going to be 0 minus 0 minus 0, which is just going to be 0. Now, this is great because if we look, we have all three components of our body force vector. We have row B1, we have row B2, and now we have row B3. So since we have the three components, we can now write it in vector form, where row B is equal to 2, 0, 0. So now that we know those body force vectors, we can move on to the main part of this problem, which is calculating that external virtual work. So if we're calculating the external virtual work for the body forces, remember this is for the body forces, this formula will not apply to the traction vectors. It's simply the integral over the domain of the summation of rho bi multiplied by ui star. You're saying, well, hold on, Clayton, you just said simply there. This does not look simple. And I agree. In this form right here, the theoretical form, it looks disgusting. It does not look fun at all. So what I like to do before I even try to substitute variables into this is I like to try and remove all of the unknowns. For me personally, the unknowns would be the integral because I don't really know what that's defined over, as well as that summation. So the first thing I'm going to do here is I'm going to say, all right, well, the grossest thing to me is going to be that integral. It's the integral over the domain. What does that mean? Well, the integral over the domain is simply the integral over the volume of this cube. So what this will be is actually the triple integral over all three directions. So if we look at our cube here, it goes from 0 to 2 in the x1 direction. So I'm going to integrate from 0 to 2 with respect to dx1. Now, it also goes from 0 to 1 in the x2 direction. So I'm going to integrate from 0 to 1 with respect to dx2. And finally, if we look in the x3 direction, it goes from 0 to 1. So I'm going to integrate from 0 to 1 with respect to dx3. So even though it looks really bad, these integrals over the domain, it's simply just integrating over the volume. And usually in these types of questions, you are going to easily know where the volume spans, basically. So it's not going to be too bad. So that takes care of the integral. But now what about that summation? Now, summations always look gross, but they're actually a lot easier to deal with than the integrals. All we have to do is substitute I into the equation however many times. So in this case, we're going from I is equal to 1 to 3. I just need to go I equals 1, I equals 2, and then of course I equals 3. So doing that, we get the following equation where we have the same integral, but now we have rho b1 multiplied by u1 star plus rho b2 multiplied by u2 star plus rho b3 multiplied by u3 star. Just like before, it's looking a lot better now because if I were to look at these three components, these three terms, I know all of the components. Rho b1, rho b2, rho b3, well, they come from my rho b vector, which we have above, now circled in green. u1 star, u2 star, and u3 star, well, we're actually given that in the problem description. So if we look at the right-hand side, I have it circled in green. We already know what all those components are. So if we're at the point where we know where all the components are, well, it's simply just plug and chug from this point. So rho b1, well, we know that's 2. u1 star, we know that's 0. So that first term is simply going to be 0. Then we add it to the second term. So rho b2, well, that's 0. U star 2, well, that's actually ax2. But again, since we have the 0 for rho b2, that's also equal to 0. And then finally, rho b3, which is 0, u3 star, which is equal to also 0, that'll be 0. So something really funny happens here. So we look at the first term, it's 0, second term, also 0, and finally that third term is equal to 0. So this is basically the triple integral of 0. And of course, you guys are really smart, so you guys know, well, the integral of 0 is always going to be 0. So therefore, our external virtual work in this case is actually equal to 0. And now if we look at our provided options for answers, we can see that option D states that the external virtual work is 0. So therefore, the answer to this question would actually be D. Now, we're done the question, but I want to leave you guys on a final note. This is the perfect final exam question. Why is that, Clayton? Why is this the perfect final exam question? Because look at how complicated it looks. We were ready to solve a triple integral, which sucks ass. No one wants to solve a triple integral. But now that it's simplified to 0, we don't even have to worry about solving the triple integral. So it's a perfect exam question where a lot of students will get scared. They'll think it's really hard, but it's actually quite trivial once you figure out that everything cancels and you're integrating 0. So that's it for question 2. I hope it helped you guys. I will see you guys in question number 3. Alright guys, welcome to question number 3, or as I like to call it, the last cuboid question, which I'm really thankful for because I'm going to be honest, I don't know if I'm saying cuboid correctly at all. It's kind of a foreign word to me, but thank goodness this is the last question for it, so I don't have to worry about that any longer. So question number 3 says, the shown cuboid is subjected to a state of stress described by the Cauchy stress tensor. So again, we have our nice 3x3 stress tensor, and this one's even simpler than before, where our only non-zero components are sigma 1, and sigma 2. Now the question says, if a virtual displacement field of u star, which is equal to 0, ax2, and 0, where a is greater than 0 is applied to the cuboid, then determine the total external virtual work. Now this is going to be a problem because, as you guys may have remembered, the total external virtual work for this cube is going to consist of the summation of traction vectors as well as the body force vectors. Now, why does this suck? Because if we look at this, there are 6 faces to this cube. That means that we have to solve for 6 traction vectors, then find the external virtual work of each one of them. And then in addition, since our stress tensor changed, we're going to have to find the new body force vectors and then find the external virtual work due to the body force vectors. So this would be 7 steps. And let's be honest, we're busy people. We don't got time for 7 steps. Therefore, there must be an easier way. Well, there is. So recall this fact right here. This is the principle of virtual work, and this is something you guys should always remember because it's a commonly used trick in these type of questions. So what is the principle of virtual work? Well, it's saying that the external virtual work is equal to the internal virtual work. Now, typically in one of these there's some sort of unknown, and then we use each other to solve for that unknown. But in this case, we're using it to say, all right, well, the question wants us determine the total external virtual work. Now, if we look at the question, we can do it. It's basically just questions 1 and 2 repeated over and over again until we cover every face of the cube as well as find all the body forces. But in this case, instead of doing that, there's a simpler way because the external virtual work is actually equal to the internal virtual work. What does that mean? Well, if I know the total internal virtual work of this cube, then I know the total external virtual work. So what we're going to do is we're actually going to solve for the internal virtual work because, as you guys are going to see, it's much easier than solving for 6 traction vectors and the body force vector. Now, the key to internal virtual work is 2 things: the stress tensor, which we have, as well as the virtual strain tensor. And we don't have that. So my first step here, I'm going to find out what my virtual strain tensor is. Now, how do we do that? Well, we're going to use our virtual displacement field. So as we are given in the question, we know what that virtual displacement field is, that u star. Now, forget about virtual work, virtual anything right now. If this question were to say, find the strain tensor from the displacement functions, you guys would all say no problem at all. I know I can find the displacement gradient, and then from there I can find the strain tensor. Luckily for us, when we're considering virtual work, it's the exact same process. So since I have that virtual displacement field, I can find the virtual displacement gradient. And if we look at the formula, it's the exact same formula where we're taking that virtual displacement field u star and we're basically taking a bunch of partial derivatives. So if we look inside here, we say, all right, I got a bunch of partial derivatives. Where do I get those from? Well, I get them from my virtual displacement field. So if I look at u star 1, which is 0, well, I know that the partial derivative of u star 1 with respect to anything, if it's 0, is going to be 0. Therefore, that first row of that displacement gradient, which is the partial derivatives with respect to u1 star, well, those are all going to be equal to 0. So therefore, my first row of my displacement gradient is going to be 0. And this is also the case for u star 3. u star 3 is equal to 0. Therefore, all those partial derivatives are going to be 0. As we can see, the only non-zero component is u star 2, which is ax2. Now, if I differentiate ax2 with respect to x1, well, it's going to be 0. If I differentiate with respect to x3, that's going to be 0. However, if I differentiate ax2 with respect to x2, I get a value of a. And if we look in the middle of that displacement gradient, or that virtual displacement gradient, as we can see, we have a value of A right smack dab in the middle. Now this is great because once we know that virtual displacement gradient, we can solve for the virtual strain tensor. And again, same formula as before, where epsilon star is equal to 1/2 of the virtual displacement gradient plus the transpose of that virtual displacement gradient. Now, luckily for us, since our only non-zero component is epsilon 2, or not even epsilon 2, the displacement gradient 2, I don't really know how to call that. We know that our virtual strain tensor is going to have the exact same form as our virtual displacement gradient. So everything is going to be 0 with the exception of epsilon star 2, which has a value of A. Now that we have that virtual strain tensor and we have our stress tensor, we can move on to the main part, which is finding that internal virtual work. Saying, all right, Clayton, well, when we talked about external virtual work, it was an ugly equation. Are you going to give us an ugly equation again? Why, yes, I am. So the internal virtual work of a continuum is the integral over the domain over the summation of ij is equal to 1 to 3 of sigma ij multiplied by epsilon star ij. So just like before, we look at this and we're thinking, this is gross, this is disgusting, I want nothing to do with this. How can we make it look a little bit nicer? Well, the first thing that we realize is, well, if we're integrating over the domain, as we talked about in question number 2, that's just taking the integral in all 3 of the directions. Basically, we're integrating over that volume. So we can change that integral over the domain as simply a triple integral. So I'm integrating over the bounds of x1, the bounds of x2, as well as the bounds of x3, basically giving me the volume of this cube. So that looks pretty good now, but then we look at the center there and say, oh, summation, well, those are kind of shit too. I don't really want to deal with a summation, so let's expand the summation out. So what we get in the end is we get the triple integral, that hasn't changed, of sigma 1 multiplied by epsilon 1 star plus sigma 2 multiplied by epsilon 2 star plus etc, etc, etc. Now, even though this looks really bad, it's actually really nice because the only parameters in this equation are the ones in the center there. And if we look at them, we have every single one of them. We have all of our virtual strains from our virtual strain tensor, and we have all of our stresses from our stress tensor. So we're actually looking pretty good. Now, luckily for us too, if we look at that virtual strain tensor, every single component besides epsilon star 2 is equal to 0. What does this mean? Well, it means that that big summation there in the center simplifies into simply sigma 2 multiplied by epsilon star 2, because again, if we look at the epsilon up there, the strain tensor, all the values are 0 except for epsilon star 2. Well, this is great because then we say, all right, well, we know those two values. Epsilon star 2 is simply A, and sigma 2 is 2x2, so I can substitute those into the equation to get the following. And then after that, it's simply just taking the triple integral. So you guys can do that in your calculator. You guys can do it in Mathematica. It doesn't really matter. What you guys will get is the internal virtual work is actually equal to 2a. Now, if we look at the question again, it says nothing about the internal virtual work. It wanted that total external virtual work. But we remember that, of course, the internal virtual work is actually equal to that external virtual work. So our answer of 2a, well, that's the answer to this question. If we look at our options, we can see that option C there, that is the answer 2a. That is the answer to this question. So that wraps up question number 3, and along everything to do with cuboids, we're going to get into something a little different for questions 4, 5, and 6. And in my opinion, they're actually a little bit easier. So I will see you guys in question number 4. Alrighty, everybody, welcome to question number 4. We're halfway done the quiz, and after this, we'll be done all the hard questions. Questions 5 and 6, as you guys are going to see, they're not too bad at all. So looking at question number 4, though, it says, the shown plate has a thickness of 1 unit and is subjected to a constant state of plane stress described by the tensor. And as we can see, we have a nice 3x3 stress tensor, and the majority of the components are actually equal to 0. So it's actually a very nice stress tensor. And the question says, when applying the principal virtual work to the plate, the following plane displacement is considered U star is equal to 0, AX2, and 0, with A greater than 0. Then the external virtual work due to the traction vector acting on edge C is given by, and of course it gives us our 4 options. Now, this question is very similar to question number 1 in that we're calculating the external virtual work due to attraction vectors. So this is going to have a very similar procedure to question number 1, except there's going to be one little, I don't know if it's a trick or one little complication would actually be the better word, that's going to make this a little bit crazy. So when we're dealing with the traction vector, the first thing that we said that we're going to want is that normal vector. So if we're looking at surface C here, remember that the normal vector is going to be perpendicular to that surface and pointing away. So if we look at surface C, we know that our normal vector is going to have the following form. So the first thing that I'm going to want to do in my calculations, I'm going to say, all right, I'm going to want to know what the normal vector is. Now, if I look at the diagram, it's very easy to tell that my normal vector is 1, 1, and 0. However, if you guys use this normal vector, you guys are going to see that you guys are wrong. And I mean that in the nicest way, because of course you guys are never wrong. You guys do such a good job, but this will give you the incorrect answer. I guess that's the nice way of saying it. And the reason why is because a normal vector must be normalized. It must be a unit vector. So if we look at n right now, it's currently not normalized. So all we have to do is take our vector and divide each component by the magnitude of that. So if we look at this vector, the magnitude is obviously root 2. So our normalized normal vector is 1 over root 2, 1 over root 2, and 0. And this is the vector on which we're going to want to base our traction vector calculations on. So now that we have the normal vector, we can move on to the traction vector. And just like before, the traction vector has a nice simple formula where it's the transpose of our stress tensor multiplied by our normal vector. So if we look at those two components, well, the normal vector, we have that right above there. It's already defined. There's no unknowns. And our stress tensor, well, we're given it in the question. It's also defined. No unknowns. So we can carry this on and say, all right, here's my stress tensor transposed, which is the same as the regular stress tensor because we have a Cauchy stress matrix. And we're simply just going to multiply that by our normal vector. You guys can do this in Mathematica or by hand if you guys want. And what you guys will see is our traction vector is simply negative 2 root 2, 0, and 0. And this works out very nicely because the more components that we have as 0, the more things will simplify later on, which is what we want. So just like before, once we know the traction vector, we can go to the real meat of this question, which is that external virtual work due to a traction vector. Now the formula for it, it's going to be the same as question number 1, where the external virtual work due to a traction vector is going to be the surface integral of our traction vector dotted with our virtual displacement vector. Now, two things to keep in mind, of course, this is a surface integral. That's where things are going to get a little bit complicated. But the other thing that I already imagine so many students doing is that dot product in between. So remember, we're taking the dot product in this formula. We're not just multiplying them, we're taking the dot product. But of course, we're going to talk about that later. Let's talk about the thing that's on everybody's mind is that surface integral. Now, as we're going to see, this is going to be a real problem. Why is that? Because our surface, in this case, is not aligned with x1 or x2. As you remember from question number 1, our surface actually was in the x2, x3 plane, which was great because then we just differentiated with respect to x2 and x3. Now, if we look at surface C here, we know it's going to be an x3 component. That's going to be no problem. It's nice and uniform in the x3 direction. But the problem is it's both in the x1, x2 plane. There's some variation there. So the best we can do at this point is saying, all right, well, we're integrating from 0 to 1 in the x3 direction. That's nice and uniform. That's no problem. But when it comes to that x1, x2 plane, well, we're basically integrating from 0 to L, the length of that surface, with respect to L. So again, this is going to be over the length of that surface. And the parameters inside don't change, where we have the traction vector dotted with that virtual displacement. Now, this is going to be a problem because although we can differentiate with respect to L, no problem, we don't know that upper limit of that integral. So what we're going to try and do is we're going to come up with a relationship between dl and dx2, because then we can substitute and make this a little bit more familiar. So if we look at surface C, we can actually define it with an equation. That is, x1 is equal to 1 minus x2. It's a nice linear line, which is what we expect because, of course, surface C is just a linear line. Now, we can take the derivative of both sides of this, and what we get is dx1 is equal to negative dx2. How did this happen? Well, if I take the derivative of 1, we get 0. I take the derivative of negative dx2 with respect to dx2, I'm just getting dx2. Nothing too crazy there. Now, where this actually comes in handy is this. We can find a relationship between dl and dx2. Because if we look here, dl is actually a triangle composed of dx1 and dx2. So the length of the hypotenuse is simply the square root of dx1 squared plus dx2 squared, which can simplify using our formula above into root 2 multiplied by dx2. Why is this so nice? Well, when we go back to our integral now, instead of integrating with respect to dl over the length of that linear surface, we can actually replace this with x2. And what's great about that is we know the bounds of x2. x2 goes from 0 to 1, so therefore I can integrate from 0 to 1. And dl, well, we know that dl is simply root 2 of dx2. So now I changed it so that everything in this new integral, it's nice and familiar to us. There should be no real questions. Now, the main thing comes down to, all right, well, the integral is good to go. But what about the components inside? Well, the first one's the traction vector. Well, we have that calculated above. That's no problem. The second one is that virtual displacement vector. Well, we're actually given that in the question description. So if we actually look at this, we know absolutely everything we need to know. Therefore, we can just substitute everything in. So again, we have two vectors in here. That's going to scare a lot of students, but realize that we're taking the dot product. So although we have two vectors right now, it's going to simplify nicely into a nice scalar equation. And it's actually going to simplify quite nicely because if we look at that dot product, it's again multiplying the first components by each other and then adding that to the two second components multiplied by each other, etc., etc. So if we look at the two first components, we got negative 2 root 2 multiplied by 0. Well, that's going to be 0. We look at the second components, we have 0 multiplied by ax2. Well, that's also going to be 0. And then finally, a third component, 0 and 0, of course, that's going to be 0. So just like before, in so many other of these questions, we're taking the integral of 0. And of course, you guys know that that's simply equal to 0. So if we look at our answers that we were provided, we have 8a, well, that's not correct, 4a, again, not correct, and 2a, not correct again. So we know the answer to this question is going to be D, none of the above. Now, I hate these type of questions because if they don't give you 0 and you get an answer that doesn't match with A, B, and C like we did here, it's always real scary picking none of the above because you really don't know if you did it right. But in this case, we did it right. We get none of the above. That's the correct answer to this question. So that's question number 4. Let's move on to question number 5. Alrighty guys, welcome to question number 5. As you guys are going to see, question number 5 is kind of the turning point in this quiz as we move from continuums over to beams. Now beams are always nice because of course you guys are civil engineers. One of your main jobs is going to be dealing with beams, so it provides a little bit more background and insight to what you're actually doing. So if we look at this question, we have a nice cantilever beam here, and it has two concentrated loads. Now the question says, when applying the principal virtual work to the shown beam, a virtual displacement y star is equal to ax1 with a is greater than 0 is considered. Then the internal virtual work is equal to. So it's a very simple question. We have a beam, we have the loads, and all it wants is the internal virtual work. So we say, all right, well, we're obviously going to start by our nice internal virtual work formula. So as we discussed in the theory, we know that the internal virtual work of an Euler-Bernoulli beam is simply the integral over the length of the beam of EI multiplied by the second derivative of the displacement function. So that's the actual displacement function. And then multiplied by the second derivative of the virtual displacement function. So we have two displacement functions. One of them is the actual displacement. One of them, of course, is the virtual displacement. Now, immediately we see that we may have a problem here because if we look, we don't know the actual displacement function. We don't know it at all. So how can we calculate it? Well, the answer right now is, well, we can't. So that creates a problem because we have an unknown in our equation that we can't solve for. So normally in these type of questions, we say, all right, well, we can't calculate the internal virtual work using the formula for internal virtual work. So what we would do is we say, all right, well, maybe we can calculate it using the external virtual work. However, this question's kind of funny. It's the first real trick question of this assignment. Because if we look at our virtual displacement function, y star, we know that y star, of course, is equal to ax1. That's given to us right in the problem description. That's why I have it circled here. Now, if we take this, a virtual displacement function, and take its second derivative, we find that d squared of y star with respect to dx squared, of course, is equal to 0 because it's a linear function. We're saying, all right, Clayton, well, the second derivative is equal to 0. What exactly does that mean for us? Well, if we loop back to the internal virtual work equation, where it's the integral over the length of EI times second derivative of the exact displacement function multiplied by the second derivative of the virtual displacement function, we say, all right, well, that second derivative of that virtual displacement function, we know it's equal to 0 because we can tell by our virtual displacement function it's actually equal to 0. Well, what does this mean? Well, this means that our integral has a 0 in it. Well, what does that mean? Well, we're basically integrating 0 yet again. So it's a very common theme over these questions that we're integrating 0, which we know is actually equal to 0. So if we're looking at the answer to this question, we know it's going to be A, the internal virtual work is equal to 0. And the reason why? Well, it's because of our virtual displacement function. If we have a linear virtual displacement function, then the second derivative is going to be 0, and therefore our internal virtual work equation, we're integrating 0, which is just going to be 0. Now, if we were given the exact same question, as you guys are going to see in question number 6 on the next slide here, we're going to see that if it's a quadratic virtual displacement equation, we can't use this trick. The reason why is because if we integrate a quadratic equation twice, it's not going to be 0. And if it's not 0, then we really can't do anything about it in terms of internal virtual work equation. All right, so that's question number 5. Let's jump into question number 6. Hey guys, question number 6, the last question of this quiz. We finally made it, and as you guys will see, question number 6, it's not too bad. It's just another virtual work question for beams, which is actually quite simple, or much more simple compared to the continuum. So if we look at question number 6, it's actually the exact same as question number 5 with one difference. In question number 5, our virtual displacement function y star was equal to ax1, while in this case, our virtual displacement function is actually equal to ax1 squared. So it went from linear, now it's quadratic. So it's not too bad, but the question remains the same. It wants us to find the internal virtual work of this beam under these loads. So we say, all right, well, if we want internal virtual work of an Euler-Bernoulli beam, we have a nice formula for it, where the internal virtual work is simply the integral over the length of the beam of EI multiplied by the second derivative of the deflection function or displacement function, and then multiplied by the second derivative of the virtual displacement function. Now, as you guys remember from question 5 before, we don't know what exactly that exact displacement function was. And what we relied on in the previous question is the fact that the second derivative of the virtual displacement function was equal to 0. And since that was equal to 0, we knew that the internal virtual work was the integral of 0, which was simply 0. But now we have a problem because our virtual displacement function is quadratic. Therefore, once we take the derivative of that twice, we have a non-zero value. So in order to solve this integral now, since we have a non-zero value, we actually need to know what that displacement function is. And we can do that. We've learned how to solve for those things, but it gets kind of messy. So maybe this isn't the best way to solve this question. So instead, we're going to utilize the principle of virtual work. We did this before, and really this is kind of a big trick in these type of questions. A lot of your guys' exam questions will utilize this trick, where they'll ask you to solve for either the internal or the external virtual work, but it'll often be the opposite of what you have to solve for. So in this case, we want the internal virtual work, but it's a nightmare to get. So instead we say, all right, well, instead of solving for the internal virtual work, let's solve for the external virtual work, because they're actually equal in this case, or in all cases. So you say, all right, well, if it's equal to the external virtual work, what's that equal to? Well, for an Euler-Bernoulli beam, the external virtual work is simply the integral over the length of the beam of the distributed load multiplied by the virtual displacement with respect to x, plus the summation of our concentrated point loads multiplied by their corresponding virtual displacement, and then plus the summation of all concentrated moments multiplied by the virtual rotations. So they say, all right, well, this is the most general form, but of course our beam has some simplification, and luckily for us, our beam has no distributed loads, so Q will be 0, or concentrated moments, so there's no big M's there. I say, all right, Clayton, what exactly does that mean for me? Well, it means that two of the terms in this equation actually cancel out, which is great because now our external virtual work is simply the summation of our point loads multiplied by their corresponding virtual displacements. So what we're going to do is we're going to take our point loads and substitute them into this equation, and we basically have two terms because, of course, we have 2 point loads. So we say our external virtual work is negative 2p, so that's our point load in the center there, multiplied by the virtual displacement at x is equal to L over 2. You say, all right, well, that's great. How about the second load? Well, our second load is simply p, so we go plus negative p multiplied by our virtual displacement, but this time at x is equal to L. So there's 2 comments about this. The first one is sign convention. It still applies even when we're talking about virtual work. So of course our 2 point loads here, they're pointed downwards. Therefore we have negative 2p and negative 2p. If you go positive, you guys are going to get the wrong answer. Luckily for us, the answers kind of indicate that it must be a negative answer. But if the correct answer, but in a positive form was there, it might trick a lot of students up. Now, the second thing is, which is probably the most confusing to most students, is what does this mean? The virtual displacement at x is equal to L over 2. Well, it's actually quite simple. If we look at our problem description there, we have it highlighted that we have our virtual displacement function, where y star is equal to a times x1 squared. And all we're going to do is we're going to take our x value and substitute it into that equation. So we say, all right, well, if we look at our first equation, we have negative 2p multiplied by our virtual displacement at x is equal to L over 2. Well, we know that, of course, all we have to do is substitute L over 2 into x1, and we get a L over 2 squared. Similarly, for the second one, we go negative p multiplied by a times x1 squared, but in this case, x1 is equal to L, so we go a times L squared. Now, what's nice for us is this simplifies quite nicely into the following 2 terms. And if we look at each one of the terms, they both have a p, a, and an L squared, so we can actually combine them into one single term, which is negative 3 PAL squared, all divided by 2. Now, this is our total external virtual work. But luckily for us, we're utilizing the principle of virtual work, which says that this external virtual work, well, this is actually equal to our internal virtual work. And the question itself, it wanted that internal virtual work. Well, now we know what it's equal to, negative 3 PAL squared divided by 2. And if we look at our given answers, we see that it's actually answer number C, negative 3 PAL squared, all divided by 2. So that concludes question number 6. And with that, it concludes quiz number 30. So thank you guys all so much for listening. I really appreciate it. Please let me know what you guys think of the new format. I'm not too sure. Again, this is for you guys, whatever helps you guys the most. If you guys prefer my sloppy writing, I will go back to the sloppy writing. If you say, no, Clayton, this actually looks a lot better than your sloppy writing, then I'll stick to this. It's completely up to you guys, so please let me know. All right? Thank you guys all so much for listening. I really appreciate it. I will see you guys in quiz number 31.